Syzygy, episode 51, Mercury in Transit. Welcome to this very special live edition of the Syzygy podcast. I mean, that's a bit of a strange thing to say because every time we record the podcast, we are live when we're doing it.
We are alive.
But the point of this is that we are live on site. Emily, sitting opposite me here in a wooden hut here at the University of York. Where are we?
We're on Astro Campus.
Awesome. And what is Astro Campus?
So Astro Campus is our observatory here at the university. It's for teaching as well as outreach. So today is a wonderful public event where people can come and view a very rare astronomical site indeed.
It is a very, very special day. What's happening today?
We've got a transit of Mercury.
Yeah, Mercury, closest planet to the sun, is going between the sun and the Earth. And we all know what that means. That's a Syzygy.
That's a Syzygy.
Yay! So not only is this a special day for astronomy, it's a special day for us here on the podcast. Very, very exciting. So, yeah, a bit of a public day. How's it been going? You've been over here for a couple of hours now.
I have. It's been touch and go. And look, the sun just literally, as you spoke, came out now, which is pretty good. I mean, the forecast at one point was saying there's at least a 50% chance of rain. Mm-hmm. So I'm going to take this patchy cloud. I've peeked it at Mercury through the clouds a few times. It's looking pretty stunning when you get a hold of it.
Yeah, I turned up a little while ago having expected to come and record this podcast and go, well, we didn't get to see the real thing. But here it is on the screen. And instead I turned up and it was not quite blazing sunshine, but it was quite nice. Yeah. And there's a bunch of telescopes set up and people are having a look up at the skies and the cloud comes over every once in a while, but the sun's just about to come out again. And when you look through the telescopes, which have got special filters on them so that you don't burn your eyeball off, I really had to gaze for a little bit, and Emily was saying, no, just look over a little bit over to sort of around about 3 o'clock on the sundial, the clock face that is the sun, and there's this little black dot, and it was there.
It's there.
Transit of Mercury. Very
really
exciting.
Cool.
Very exciting. How many transits of Mercury have you seen?
Transiti.
How many transits of Mercury have you seen, Emily?
This is my second.
Your second.
It is. Mm-hmm. So 2011, we also had a transit of Mercury, which I was able to catch. So, I mean, I love Mercury. We've spoken about this before, how Mercury is my absolute favourite planet. So, you know that this episode is all the way up my street.
Yeah.
Getting to see Mercury.
Yeah, it's
live
pretty cool.
in its tininess.
It's pretty cool. Okay, I don't think I've seen Mercury before. Pretty sure I saw... When would the last transit of Venus been?
2012.
2012.
That was
pretty
a
sure I
hemisphere
did that one. Yeah. Oh, look, and the sun's just coming through. The sun's very low in the sky because we're coming towards winter here in the Northern Hemisphere. And so it's dappling through the trees, falling onto at least one of the telescopes around Astro Campus. It's really nice.
That's right.
Given that the forecast was just horrific rain that we've had here in Yorkshire for what feels like eons, this is actually really quite nice. Yeah, so I think I've seen transit of Venus before, but not transit of Mercury.
Yeah. So the last transit of Venus in 2012, we set up a massive schools project. I was in Christchurch at the time, and it was the 6th of June 2012. It's a day that I'll never forget because we set up this enormous project. We had children bussing in from all around the district. It was going to be big live screens. We're going to have 16 different solar telescopes. It was enormous anyway. And the morning of, I woke up and I thought, it's quite cloudy. By about 8 o'clock that morning, I thought, it's looking quite white out there. And it doesn't snow super often in Christchurch, but we had an enormous dump of snow.
This was like act of God style.
It was just like, you shall not transit.
Yeah, someone didn't want you to see this.
The university closed, the buses couldn't run on the roads, there was too much snow, it was just chaos.
Oh dear.
So I spent the last transit of Venus in my pyjamas in front of a computer thinking, I wish it was sunny.
There are worse ways. I mean, in your pyjamas at least. That's not too bad. So today, it's not about Venus. It's all about Mercury, which is very exciting. Mercury and Venus, this is going to sound like a really stupid question, they are the only two planets that we can see a transit of.
That's
right?
exactly right.
Yeah, because Mars is on the wrong side.
Yes.
If we see a Mars in transit, something's gone very, very wrong.
Yes.
Right, good.
But you can see other things transit.
Like
you can
what?
see the moon.
Well, that's true. We would call that something else.
And we call it an eclipse.
Yes.
You can also spot the ISS if you're very clever.
Yeah, you see these amazing photos of what is presumably using one hell of a filter in front of your camera, but picture of the sun with this really quite severe outline of the ISS sitting in front of it, which is quite a startling image because it kind of looks like the ISS is about to plunge into the sun, but that's not happening.
No, it's fine.
Yeah.
And even last year, some of my students managed to catch a picture of an aeroplane transiting the sun through one of our solar telescopes.
Cool. So anything passing between us and the sun is both a transit and a syzygy, although a syzygy, I guess, strictly speaking, is sort
celestial
of celestial
bodies.
bodies.
Yeah.
Transits, you could probably make the same argument. Anyway, today it's all about Mercury.
It is.
How many people have you had coming through here?
I would say it's on the region of 200 so far. Yeah, it's been fantastic. It's just a drop-in kind of session. The whole transit of Mercury takes about 5 to 6 hours.
Yeah.
So we didn't want to be like, you've got to show up at 2 o'clock, otherwise you might miss it. Also because the weather is really not that predictable.
Yeah.
So about 12:30 for us, the transit started, and we've just had people dropping in, checking out beautiful little Mercury.
Okay, so assuming, this is a podcast is an audio thing, although, of course, we do tend to put pictures up with the podcast. So if you're listening to your podcast on an audio player, which will show you pictures, have a look at the pictures. But if we were here looking through a telescope, what would we be able to see with a transit of Mercury?
So on the first impressions, it's actually rather unimpressive. Mm-hmm. We have to remember that Mercury is not only a super tiny planet, but it's quite far away.
Yeah. I mean, it's... Okay, so can you lay this out for us, right? We've got the sun and the Earth. There's our length scale, and that's what's known as an astronomical unit, if I'm not incorrect. The average distance between the sun and the Earth, that's one astronomical unit. How far away from the sun is Mercury?
So it's about a quarter
About
of
a
the
quarter.
distance, and we are plus or minus a bit. But
Okay,
yeah.
so it really is in there quite close.
Yes.
Right, there's 3/4 of the distance between Mercury and us, and 1/4 to... Okay, and as you say, it is very small.
It is very
And the
small.
sun is very large by comparison.
It is.
So it's not going to be like seeing an eclipse.
No.
Right.
So for an eclipse or even for a transit of Venus, you can look at it through your own eyes with solar glasses. But for Mercury, you really need the magnification of a solar telescope. So that's why we've got all our big lenses out. We're pumping up the image. And even then, Mercury's only 1/194th the diameter of the sun.
Call it 1/200th, and we're done.
But I'm an astronomer. I like to call it 100.
Roughly, you're an astronomer. We've talked about this before, Emily. You're working in a field where the error bars can be quite large, where the uncertainties can be quite large.
We were able to measure this so precisely.
Yeah,
so
I mean,
nice.
I guess if there's one thing that we do know about, it's the sizes of things in our own solar system. So you're absolutely right. But let's call it, for the sake of podcasting, 1/200th of the diameter of the sun, which is not big.
It's
And
really
looking through
tiny.
the telescope before, there was a big red blob, which actually took me a little while to actually figure out, that's the sun. I thought that was just the entire field of view of the telescope. I was like, where's the sun? No, that is the sun.
Yeah.
The big red thing is the sun. Okay, so where's Mercury? It's that tiny little black dot there. Oh, wow.
Yeah. So if there'd been some sunspots, which there aren't really any sunspots today, but if there had been, then often Mercury is a lot smaller than sunspots.
Wow. So it's smaller even than common surface features on the sun.
Yeah.
That's fairly impressive. Okay, so how long does it take to go across? How long did you say it
So
took?
between 5 and 6 hours, depending on where you are
Yep.
and that kind of stuff. We've got some time. Mercury's, chilling out on its way across.
Yeah, although, unfortunately, we're also not too far away from sunset
Yes.
here.
So we're
here
not
in
going
New
to
York.
see the end of it, unfortunately.
No. But with any luck, I mean, I'm looking out now, the clouds are they're passing by. We might get a little bit more telescope time. You never know. All right, so take us through a transit then. Because you get different features as you go along. Some of the more interesting parts of a transit. I mean, once Mercury's sort of going across the face of the sun, it's basically, it's a black dot there. Oh, now it's moved along a little bit. Now it's a black dot there. But some of the more interesting bits are when it actually approaches and then one side and then leaves the other side.
Yep.
So talk us through a transit.
Yeah, okay. So there's 4 important points that we have in the transit, and this is actually true not only for transits of Mercury or Venus in our solar system, but we use exactly the same terminology if we're talking about exoplanets, which is very exciting. So there are 4 contacts. They're called first contact, second contact, third contact, and fourth contact. we weren't super creative that day.
Yeah. But then again, this is the sort of thing where you don't necessarily want to come up with really inventive names, because then people just have to say, what's that? Oh, it's point of first contact. Oh, why didn't you call it that? Like, for once, the astronomers have got that one right. I think.
And they do sound quite cool. So first contact, which is clearly the most exciting one.
Sure. It's happening. It's happening now.
Is when you basically, Mercury just touches the edge of the sun.
How well defined is that? I mean, Mercury is a small lump of rock, so it's got a pretty well defined edge. It doesn't have a big thick atmosphere to haze things out, so that's fine. The sun, though, the sun in my mental image is a bit fuzzy around the edges.
It
and
is,
if you're talking about something as small as Mercury, I would have thought the fuzziness of the sun, like when do you get to the edge?
It's quite difficult to measure. And depending on what filters you're using on a solar telescope, it can look quite defined. So the telescopes here, we have hydrogen alpha filters, which means it blocks out like all the blue light, for example. So it does look like a sort of a quite crisp edge, but that's just an illusion. The sun, of course, is kind of quite nebulous and gassy towards the edges.
Right.
So it can be tricky to measure that. But so what we do tend to measure a little bit more precisely is what's called second contact, which is when all of Mercury just squeezes inside the disk of the sun.
Okay, so if it's a little bit difficult to define the absolute outer edge of the sun, you definitely know when it's inside that disk.
Exactly.
Okay, so that's the second contact.
Yep.
Okay.
And yeah, you can probably guess what third and fourth are.
I'm guessing it's if you played that tape backwards and you got Mercury popping back out again on the other side.
Yep.
So hitting the inner edge or the sort of the inside of that disk and then leaving the disk entirely.
Exactly, yep. So for us, for example, there was about 2 minutes between first contact and second contact.
Wow, that's pretty quick.
Yeah.
Yeah.
But that's because Mercury's tiny.
Yeah, well, as we've pointed out.
Yeah.
Yes. Yeah.
So in universal time, we're expecting the whole transit to last from up until about 6 o'clock universal time, which is the same as UK time at the moment.
Okay. And is that coincidence? Like, did they sort of go, well, we need a universal time so that all astronomers can speak the same time language, and let's just make it Greenwich Mean Time just for the sake of it?
It is. That's exactly the reason. It's just that Greenwich Mean Time is slightly different from universal time because it had a few errors in it. So we fixed that.
Okay. So universal time is Greenwich Mean Time once they've fixed up the errors.
Yes.
Right.
Exactly.
Well done all. Okay.
So today we've got a lot of, hopefully lots of people around the world joining in on the transit of Mercury. Most people around the world can actually see this transit at some point or another, provided they've got nice weather.
Yeah, I was listening back to one of our earlier episodes. We were talking a little bit about transits and building up to this episode. And I asked what now seems like a really silly question, which is, would people all over the world be able to see this? Because an eclipse of the moon, or a lunar eclipse, solar eclipse is the word I'm looking for. A solar eclipse where the moon passes between us and the sun. That's not seen everywhere. That's generally a very localized thing that's only across one band of the world. And so in my mind, it wasn't such a stupid question. But as you quite rightly pointed out, but you know what? Mercury is between us and the sun. So if you can see the sun, you can see the transit of Mercury. So, that kind of makes a lot of sense.
So it's a much shorter list to say who can't see it.
Yeah, and that will be places where it's already over or it hasn't yet started when the sun is properly in the sky. Yeah.
So we've got Indonesia, a little bit of Asia, well, sort of about half of Asia, and, Australia,
SOS, guys. But, that's all right because we're here doing it on your behalf. I kind of feel like we're representing.
Yeah.
Yeah.
And you can always get the next one.
Yeah, which is when?
2032.
That's not so far away. That's like, what's that, 13 years?
Yeah, so there's about 14 transits in a 100-year time frame of Mercury.
Okay.
So, on average, you're waiting a little bit less than 10 years for the next one. Yeah,
and that's because Mercury is winging its way around the sun much faster than any of the other planets. Its orbital period is much, much faster. I mean, how long is the orbital period of Mercury?
88 days for Mercury, yeah.
So it's coming around far more often, and so there's just many more chances for it to pass in front of the sun.
Yeah. But it turns out that even though it's whizzing around quite quickly and it passes in between us and the sun quite often, transits are still pretty rare because it tends to miss the sun quite a lot.
Now, what do you mean by that? How
so
does that
if
work?
you took two pieces of paper,
Yep.
imagine this. So the first piece of paper is the orbital plane of the Earth as it goes around the sun. right?
Yep.
Now, your second piece of paper, if you tilted that at a very small angle and intersected that with your first piece of paper.
Okay. Yes. I've got my two pieces of paper, one intersecting the other, and it's a slight angle, so it's a slight lift of one side, drop of the other side.
And if you drew a circle on that, there's only 2 points in that circle where the two planes or two pieces of paper intersect.
I see. So, am I right in thinking that one of those pieces of paper, that's us going around the sun? That's our plane of orbit. So the Earth is going around on the surface of one of those pieces of paper. That's our plane. The other one, tilted slightly, is Mercury.
Yep.
Both going around the sun in the middle, but not on the same plane, not on the same piece of paper.
Yeah.
And so they only line up in the same line twice on each, or they're only in the same plane twice on each trip around for Mercury. So even though Mercury, as you say, even though Mercury is going around every 88 days, it's actually fairly rare for that to coincide with, quick, look at the sun, it's in transit.
Yeah. Those special points, by the way, are called nodes.
Oh.
So there's two intersections. And so what you want to have is a node at the same time as Mercury's going in front of the sun, or between us and the sun.
Which, that wouldn't happen particularly often.
No.
No.
There are two nodes. They're called an ascending node and a descending node.
Ascending, descending, that's up and down. How do you define up and down in space, Emily? I thought the whole point of space was that there wasn't an up and a down.
Well, we basically assume that we're the flat ones and Mercury goes up above and then below.
Okay,
and,
it's all very Earth-centric, as usual.
Yeah, so we're currently in an ascending node, which means that transits tend to happen in November time, which is interesting.
Okay. Okay, so, I mean, I'm looking out across Astro Campus. There's a bit of a crowd over there now. There's been people coming and going. You've made, quite understandably, a bit of a big deal about this. You were in the press today. You were having a chat with the radio. We've got a little video out there on social media. Astronomers, I can understand why you would get interested in something like this. This is an astronomical event. It's rare. It's rare enough for you to get excited about. But it's a bit more than that. Why are we interested in this? Why do we care?
Well, in some ways, we can attribute the whole mapping of New Zealand by James Cook to the fact that we really wanted to observe a transit.
All right, take us on this little journey. Take us on a journey with James Cook.
Okay, so we're talking about the 1760s. And in this time, then, the Royal Society, who was kind of in charge of all scientific knowledge in at least in England and the UK, they were really keen to do some better measurements of the distance between the Earth and the Sun. Mm-hmm. That's a really hard thing to measure, especially if you're back in the 1760s.
Not easy, no.
It sounds like it should be easy, but it's really not. We've got Kepler's laws, which tell us things about how quickly the planets are orbiting the sun, but you need to have one concrete measurement because the rest are all just ratios.
Yeah. I mean, you can see, you can measure the angular extent of the sun in the sky, okay? And did we at that point, we had a well-established knowledge of the size of the Earth. There are other ways that you can do that.
Yeah.
But without having something to nail it down, as you say, all you've got is ratios. You need something that allows you to say, good, we have a number, we can now do the conversion of all the others, rather than just saying, for example, Mercury is 194th. Was it? Is that the right number?
Yeah, that's
194th of the diameter of the sun.
Yeah.
But that doesn't tell us the size of Mercury or the sun.
No.
Okay, so what do you have to do?
So you need to make a concrete measurement using the fact that you stuck on the Earth, basically.
Right.
And so what they were interested in doing is triangulating, basically, the position of Mercury or Venus. Venus was the easier transit in some ways to get. So you can triangulate by observing the planet from at exactly the same time from two different locations.
Ah, okay. So what you're doing is, when you say triangulating, right, you're looking at it from two different locations on the surface of the Earth, and you're looking for slight differences in timing or slight differences in angles at that same time, which you can then crank the calculation backwards to say, aha, so this means it must be this far away, because that's how all the triangles work.
Yep.
Is that it?
Exactly. And if you were able to measure very precisely your own position on the surface of the Earth, then you can actually do this without a transit. You can just measure the position of the sun, for example, and then be able to back calculate that.
Right.
But again, in the 1700s, getting your precise location, particularly longitude, was really hard.
Really hard. Yeah. There's some amazing. There's a book called Longitude, which by Sobel, is that the name of the author? I think we'll put it in the show notes. Really, really interesting read because it points out just how hard that problem was to solve. It took technology that you'd think surely there's a way to do this. No. So that was a very difficult thing to do
Really
back in
difficult,
the when are we talking? The 18th century, 1700s.
Yeah.
So you can't just use a single measurement or a single observation like the sun. You've got to use something like Mercury or Venus going across the face of the sun.
Yeah, and you can time those. You can time, say, the position of second contact and time the position of third contact. And even if your clocks are wrong, at least between your two locations, so long as your clock keeps time to itself, you've got the duration of the transit and you can back calculate much more accurately.
Right. So you're looking
at
differences at that scale of different places on the Earth will see very, very slight changes in, for example, the amount of time it takes Mercury to get across the face of the sun and enter one side and leave the other side. And even those tiny differences are measurable in the 18th century.
Yeah.
To be able, so that we can figure out how far away the sun is.
Yeah.
I mean, that's quite extraordinary.
So this was a major undertaking by the Royal Society, and they said, right, we're going to do this. We've got to figure out how to do it next. So they've got to send some astronomers to the other side of the world.
And that's not just a matter of whacking them on a plane, cattle class, not business class. We wouldn't pay for that. But you can't just, there was no easy way to get around to the other side of the world. This was a major expedition at the time.
Yeah.
And so while we're at it, we may as well pick up a couple of countries along the way.
Yeah. So Captain Cook's main mission was to go to Tahiti and observe the transit of Venus. He took along, he was quite a good astronomer actually himself. He was very, very well versed in how to navigate using the celestial pointers like stars and things like that.
Grew up not terribly far away from where we are here.
Well, exactly,
actually.
yeah.
Yes,
it's quite
up here
nice.
in Yorkshire.
We're quite in his hometowns. So he also took another astronomer called Charles Green with him as well as a backup. So they both did the measurements. They had a fantastic time, by all accounts, who knows, in Tahiti. Did their measurements anyway, they needed to. And then they carried on. And then it turns out when their sort of secret mission, if you like, or the second part of their mission, was to go find out a little bit more about this great southern continent that may or may not actually have been there.
Yeah, so you look at the maps from the time and there were sort of little hints of something in the realm of, the southwestern Pacific, coming down from Indonesia, which was quite well known. But there's a little hint of northern Queensland or something, a little hint over in the west of Western Australia. But there's a big void in between, and that's a very large space to leave empty on a map.
Yeah, so there were some reports by, for example, Abel Tasman, Dutch navigator who'd sort of seen a bit of what's now New Zealand. Of course, the Māori people were already there; they knew all about it.
Yeah. They'd figured that one out.
Yeah. But at least Westerners had sort of only just come to the party on the fact that it exists down there. But there was also another transit coming up. So as part of Cook's mission, when he was carrying on, was to also observe a transit of Mercury.
So Venus was in Tahiti.
Yep.
Where did Cook and co. check out Mercury?
Well, you're going to love this.
Yeah.
From the Mercury Islands and Mercury Bay.
Of course they did. What a coincidence. That's amazing.
Because Cook was just naming stuff, right?
Yeah.
So,
what do we call this island? I don't know. It seems appropriate. Let's call it Mercury.
Yeah, so this is all in 1769, sorry. And he was in the part of the Coromandel Peninsula, which is in the North Island of New Zealand. And he found this beautiful beach, sit up there to observe the transit of Mercury. It's now near Shakespeare Point. And it's honestly stunning part of the world.
Lovely bit of place.
If you haven't been, Whitianga is the closest city or town. It's just a gorgeous part of the country.
So Cook was choosing in the way that I think scientists tend to do. Scientists like to congregate for conferences and things in nice parts of the world. So Cook was just ahead of his time in that regard. Let's go to Tahiti, go to the North Island of New Zealand, check out a couple of eclipses, a couple of transits, and then I don't know, claim a few spots of land for the government back home.
Yeah, I mean, not everyone saw it
No, they
from
didn't.
that perspective,
They
but
didn't.
the measurements were successful, let's
Yes.
at least say.
So from a scientific point of view, great thing.
Yep.
From a colonising the world and taking over cultures that previously existed, not so great. But let's push that aside for the moment
Yep.
and concentrate on the astronomy.
Yeah, so him and his astronomer on board carried on, and actually, unfortunately, Charles Green, the astronomer, died on the way back, but the measurements carried on.
Occupational hazard of being an ocean-born astronomer at the time. These are very long trips.
Yeah, I think he got dysentery or something fairly nasty,
nasty.
In Australia, I believe, but not saying anything there. But yeah, so he was actually an astronomer from Yorkshire as well, so
All right.
it's all rather
There we are.
coincidental.
There we are.
But it did mean that Green's notes, it took people a while to look at them because he died and he'd maybe not made the best of notes.
Wasn't feeling top of his game at the time.
Maybe anticipating that he would be the one to sort of do all the calculations. But they eventually did come out and they were able to calculate the distance to the sun.
And how good was that? How good a calculation could you get in the 1770 something?
Well, it's certainly an order of magnitude of what had happened before.
Mm-hmm.
So they were able to do, get it much more precise. I mean, they were at least 20 to 30% off previously. I'm
Wow.
not sure how well they managed to get it down after the transit, but enough so that it was a success.
Yeah. Wow, it's amazing to think that before that we really had such a rubbish idea about how far away the sun is. Then again, it's a really difficult thing to do.
Yeah. So in modern times, we're pretty good at it.
Yeah.
We just use radar, which means that we bounce light or radio signals that's more commonly off the surface of the sun. Yeah, light's not really going to work in that example.
No,
is it?
yeah, pushing uphill there. But
Radio signals.
like that's fascinating that you can just, well, let's just throw some radio waves at the sun, wait for them to bounce off and measure the return time. That's very cool. It's probably a little bit more accurate than observing
Very
in the
much so,
1700s.
yeah.
Although, with the sorts of equipment that you've got here, you'd probably be able to improve on Cook's measurements from the time anyway. Their telescopes would have been good, but not great.
Yeah.
know.
In fact, so when they were making these measurements, both Cook and James Green were, I'm keeping on James, it's Charles Green, but they were making, particularly for the transit of Venus, they had timings that were quite different from one another actually in the end, which didn't help, I guess, some of the confusion. But one of the problems they encountered was something called the black drop effect.
Black drop, okay. Tell me about the black drop effect.
So the black
Sounds
drop,
important.
It's quite cool. It's an optical illusion, or at least partially an optical illusion, whereby if you're looking at second contact, for example, and you're trying to measure the exact time that Mercury or Venus leaves and is not touching the edge of the sun anymore, when it moves a little bit away from it, it seems like there's kind of this black smudge which connects the planet back to the edge of the sun.
Okay, so it sort of smears out or changes the shape. It's as you say, it's an optical illusion. So it's not a little dot or a disc anymore. It's
Kind of like an
warped.
elongated sort of
Right.
blob that extends out to the edge of the
What
solar
causes
disk.
that?
Well, we're not 100% sure all the reasons. Some of them are dodgy optics from old telescopes,
Right.
That's part of it. But we have actually observed the black drop from space as well.
Okay.
So it's not 100% that. For us on Earth, I mean, the atmosphere gets in the way, it muddles things out, so maybe it kind of enhances the effect. But there's probably at least something to do with the limb darkening of the sun that's involved.
The what?
Okay,
The
so this
who?
is the edge of the sun appears a little bit fainter than the centre of the disk.
Okay.
This
Is that because we're the sun is not a disc, it's a ball, and so is it because you're sort of looking through the atmosphere?
Yeah,
in a
exactly.
sense?
You're looking through more atmosphere at
Right.
the edges, so it appears a bit darker than the centre of the disk. It's actually, you can't really see that with your own eyes very well. We do have some, one of our labs here actually for our students is to measure that effect and characterise it. But maybe that's, because it's a bit dimmer on the edge of the disk, maybe that's contributing to these measurements. How it was interpreted, at least for Venus back then, was that it was thought that this is evidence that Venus has an atmosphere.
Oh, okay. Okay, so the atmosphere around, so you might see Venus as a pretty solid disk as it's going across the sun, but when you get to the very, very edge, you'd, presumably see some kind of, not interaction, because it's still a very long way away, but an optical
fuzziness,
intellectual,
yeah.
a fuzziness of the atmosphere of Venus and maybe the atmosphere of the sun, playing off each other optically. Interesting.
It's actually not that at all.
Okay,
but
right.
I mean, Venus
Sounded
does
good.
have an atmosphere.
Yeah, Mercury doesn't.
But yeah, the evidence they had was not the right, because Mercury does exactly the same thing, and Mercury doesn't have an atmosphere. So.
Mercury has a black drop effect.
But we used it at the time.
So jury's still a little bit out on that one, but it is there.
Well, it's interesting.
Yeah.
And then I guess the other historical one that's quite interesting is that good old Kepler got involved in transits.
Oh, really? Okay.
Yeah.
Why?
So this is Kepler, the astronomer from the 1600s, rather than Kepler, the space telescope.
Yes. Yeah, a different one. It wasn't looking at transits. Well, it wasn't looking at transits of Mercury. It was looking at other
transits. Isn't that interesting?
Yeah,
anyway,
how it all comes together. Anyway, Kepler, back in, what did you say, the 16th century?
Yeah, so in 1627 he did a calculation.
17th century, yep.
Yeah, he did a calculation about transits. So Kepler's laws are named after him because he was able to characterise the orbital mechanics of the solar system in a much more accurate way than anybody else ever had.
He came up with a few laws about the relationships between how long it takes something to go around the sun and how far away it is from the sun and those sorts of things, which ultimately helped Newton and others sort of bring it all together into, you know what's going on here, right? We have got this theory of gravity, and you can put it all together into one coherent theory. But before that, Kepler did a lot of the background work on, look, if you observe all of this stuff, there's some patterns here, and they're really good patterns. So he came up with those. So what was he doing with transits then?
So he was predicting them based on all his calculations.
Okay.
And he managed to predict that both Mercury and Venus would transit within a month of each other. And this was in 1631.
And he was right.
He was right, yeah.
Look, you don't have to go back terribly far. And in fact, even today, some of these things are still considered by certain members of the public as magical and mysterious. So the notion of being able to go, no, I've got numbers and I can tell you when it's going to happen. It's, in a way, amazing he wasn't burnt at the stake for that. Some people would have.
Yeah, I mean, it's really good. He was really cautious about his numbers too. He said, okay, everyone, we're going to start observing like 2 or 3 days beforehand, just in case, because I'm not 100% sure that I've done the maths right, I'm not 100% sure my input values are correct enough. Because remember, this is 150 years before we knew the distance to the Earth and the Sun super accurately.
Yeah.
So all these things play roles in creating uncertainties.
Yeah.
It turns out he was actually correct within 5 hours.
Wow.
Of the transit.
That's pretty good in the 17th century.
That's pretty good for a bit of pen and paper. Yeah. So that was really nice. Unfortunately, Kepler didn't get to see those transits. He died in 1630.
That sucks. You do all the work, and then you don't get to see it. So how far apart did you say they were?
Less than a month.
That's amazing. That can't happen terribly often.
No, I didn't do the sums on how often that happens.
But that's got to be really rare,
Really,
right?
really rare, because
so
Venus
that
only happens
doubly
a couple of
sucks
times.
to be Kepler, to go, okay, hang on, wait a minute, I've done all of this work. That must have been years of work in order to get the data to be able to come up with these laws, Kepler's laws of planetary motion, of orbital motion, to then work through it and go, I reckon that there's going to be a transit of Mercury and of Venus within this really short period of time, and it's not in 400 years' time. It's coming up just down the track. Oh no, I've died. That's just not fair.
It's not really. He didn't get to see how accurate he really was.
All right, someone should name a space telescope after him or something, I reckon.
If only.
Yeah. Poor bugger. That's not fair.
So, of course, the reason why the Kepler Space Telescope is named after Kepler is because it actually does do transits.
Yes. So transits are not just something that we see in our own solar system. We see them elsewhere as well.
Yes.
Yeah.
So transits are when, for example, an exoplanet happens to orbit in such a way that it passes between us and its host star.
Again, a syzygy. Ping!
Whee!
Yeah.
So these transits are measured, and we measure just a almost imperceptible drop in the amount of light that we receive from a star. We don't get to see the disks of stars like we get to see the disk of our own sun.
Right.
So all we're just measuring is basically a little drop in the amount of starlight that we're getting. So this links into why transits are still important to us today. So there are lots of astronomers measuring this transit today, and some of them are measuring them for the purpose of refining the models that we have on how planets transit stars.
Okay, yeah, I can see that, because if you can understand to another decimal place or two, how the optics, how the transit of Mercury or Venus looks from the Earth, how that works, then you can apply that knowledge to, all right, if we look at a star a very, very long way away, which is it's no longer a disk, it's a dot, but we can see that dot dim a tiny, tiny, tiny little bit, that helps.
Yeah,
that all
it definitely
helps.
does, yeah. And it's also the contacts, which are quite important. So measuring, we do see the first and second contact, for example, in an exoplanet transit.
Really?
Because that's when you start to see the dip, and then the dip becomes at its lowest.
Yeah,
In a perfect world, you get a flat bottom at that point as the planet's transiting, and then it comes back out
So
again.
if you imagine, and again, check an image in the show notes, we'll throw one in, but if you imagine sort of the brightness of the star as a line going along a graph, and then it starts to dip, and that start of the dip, that's first
Contact.
Yeah. And so it dips down, and then when the planet is in front of the star, it's going to be blocking out basically the same amount of light as it goes across the star. And so you reach this lower plateau, this minimum for the brightness.
Yep.
And so first contact is where it starts to dip. Second contact is where it stops dipping and reaches.
It's like an upside-down trapezium.
Very clever. And then, of course, coming out the other side, starts to go back up again in brightness. So that's third contact.
Yep.
And then reaches maximum brightness as fourth contact.
Exactly.
Brilliant. So if we can observe first, second, third, and fourth contact with Mercury and Venus really, really well, we can understand more about that.
Yeah, because it turns out stars have similar physics to the sun. I mean, they have limb darkening and all these other effects that mean that we don't get these beautiful straight graphs in reality. Reality, they're a lot messier.
Yeah.
And so we need to input lots of physics to understand them.
Very nice, very nice. So this isn't just an excuse for a bunch of astronomy nerds to get out and freeze to death on a cold Yorkshire afternoon waiting for the clouds to part. This actually really does have import on current, like right now, astronomy research.
Yeah.
Cool.
And in the past, it's been used for lots as well. So we've looked at gravitational interactions between the sun, the Earth, and the moon. Mercury, for example, is the only planet that you can observe general relativity, or at least the effects of general relativity on.
Yeah. So to a very large degree, Newton's laws, Newton's mechanics, works really, really well in the solar system. But Einstein's theory of gravity, Einstein's relativity, kicks in when you've got really strong gravitational fields. And Mercury's close enough to the sun, and the sun's really big. Mercury's really small. So Mercury's orbit, it's close enough to the sun that you can start to see measurable relativistic effects.
Yeah.
That's
so
cool.
It's the only planet we can measure so far, at least. Those effects.
I mean, we all have, relativistic effects at some level, but they're just really, really small. But Mercury is big enough that you can actually observe that.
Yep. Transits have also been used to calculate the mass of Venus by similar gravitational effects.
Cool.
And even the size of the sun. And does the sun's size vary? Because the sun isn't just a blob that sits there in space doing nothing. It's this hugely dynamic nuclear fusion reactor that changes brightness, that changes temperature over time. So we're really interested in monitoring that.
So if you've got a sense of how big the sun is, you can predict, okay, so this is what the transit of Mercury is going to be like today. And if it's slightly different from that, you've then got information about, well, maybe that's the sun. Maybe the sun has changed a little bit. Let's look at that a bit closer. That's cool.
So it's all fun. It's all really cool.
Yeah. Things are getting a bit quieter here on Astro Campus. Still a few people wandering around hoping to see things, but the clouds are... What do you reckon, Emily? Are we going to get any more?
We're competing against two forces of nature against us right now. We've got not only the clouds, but we've also got the trees, which are starting to block some of the sun's light.
There's only so much you can do. I mean, I think chopping down the trees would be a bit extreme. There's not much we can do about the clouds. And eventually, there's not a hell of a lot we can do about the rotation of the Earth on its axis either. The sun's going to set in the not too distant future. I don't know. Do you reckon we're going to see it again? I think we might be done.
I think we might be done, but there's always the online, there's some wonderful things online. For example, Virtual Telescope Project is a great place to go and have a look at live astronomical events. If you missed this one, then they keep in track of lots of different exciting things.
And I'm sure they'll have a recording of it up there if you want to go and relive the excitement of first, second, third and fourth contact.
Yep, see if you can spot and see if you see the black drop.
And guaranteed it'll be all over YouTube, There'll be no problems finding it. So, okay, before we find our way out of this episode then, Emily, Any last comments? Anything else we need to
I
do
just got
before we say goodbye to Mercury?
one last piece of trivia for you.
Go on then.
So what is the closest planet to the Earth?
Closest planet to the Earth. I kind of feel like this is a trick question, but I'm going to go with the obvious answer, which is I reckon it's Venus.
No, it's not Venus.
It's not Venus?
It's not Venus.
Mars then.
On average.
On average. This is a trick question. I'm guessing that because we're talking about Mercury today, it's Mercury?
It is.
It is Mercury. Really?
Mercury is the closest planet to the Earth on average.
Get out of town.
Well, because if you think about Mars, for example,
Yeah.
we say that that's our nearest neighbour, and
Yeah.
it's the planet that comes closest to us in
Right,
some sense.
okay.
Right, when it's
So
direct-
I was
directly in
completely wrong when I
opposition.
said Venus. I should have said Mars. Okay.
Yeah. So when it's in opposition, it does come closest to
Sure.
us, but then it goes to the heck the other side of the sun.
Oh, yeah, okay. So Mercury is further away than Mars can get all the time.
Yeah.
But it's closer than Mars gets for much of the time.
On average.
Is that a way
on
of saying
average,
it?
yeah. So the closest astronomical object, apart from the moon,
Yeah.
that we are to in the solar system, is the sun, because we're always the same distance from the sun.
Sure. Well,
Everything
okay,
else
yeah.
moves further away from us than
And
the
so
sun.
the next one out, if we're going to talk planets, has got to be Mercury.
It's Mercury.
It throws you for a loop, doesn't
So
it?
it turns out that Mercury is our little buddy neighbour.
So is that true for all of the planets then?
It's all of the planets. Mercury is the closest planet. on
Mercury is the
average.
closest planet to
To
all
all
of the planets.
yeah.
That's nuts. Okay, that one is for your next dinner party. Just whip that one out. You know, when there's a lull in conversation, here you are. Look, tell you what, what's the closest planet? And you'll get a nice one. Well done. All right, well, that does bring us to the end of this Mercury-filled, if that's allowed, Mercury-filled episode.
You've got to be
Syzygy.
careful there.
Yeah, because you shouldn't play with Mercury. You know, when I was at primary school, back in the day, which was sort of late 70s? God, is that true? Late 70s, early 80s. I can distinctly remember not many science lessons, but one of the science lessons was our teacher bringing out a little bottle of mercury, opening it and saying, come on, kids, play with this. And we're sticking our fingers in it and rolling around the table. Because mercury is an amazing, amazing metal.
Yeah.
It's also really poisonous. And he really shouldn't have done that. But it was one of the only memorable science lessons that I had from a kid.
It used to be used a lot to hold up the mirrors on telescopes.
Really?
Because it's a fluid, but it's incompressible, and it doesn't change with temperature changes.
Wow. And so
And I've got
did
a
you get
good
a
story
lot of...
about that.
Oh, really?
But we're going to save that for a special episode.
Save that for another time. Did you get a lot of dying astronomers, though? Was that...
Well, let's just
Mercury
say that
poisoning?
not all of them left the telescope dome the same condition they went in.
Nasty. We'll save the rest of that story for another time because we do have to finish this one up. Listen, if you want to get in contact with us, there's a whole bunch of different ways that you can do that. Emily, how do people get in contact with us?
So we're on Twitter. I've been
We are.
throwing out a few pictures today.
You
to
have.
The Twitterverse.
You have.
And
been very
that's
good.
at SyzygyPod,
Indeed.
SYZYGYPOD.
Yeah, but that's not the only social media that we're on, is it?
It's on.
No.
We're on all of the others.
Well, many of them anyway.
Okay.
The ones that
The
matter.
ones that matter.
We're on Facebook. Just go and search for Syzygy Podcast. We're out there somewhere. We're on Instagram.
We have
at
to be
SyzygyPod.
beautiful pictures.
Yeah, because as we've mentioned before, astronomy is a very, not exclusively, but definitely a very visual medium.
Yep.
You can also go to syzygy.fm, which is our website. You can find all the past episodes, all the show notes, the works. Just go and binge on some astronomy and find us there. But otherwise, we're going to have to pretty much wrap it up there. So we'll catch up with you in, give or take, a week or two's time. So until then, catch you later.
See you later.
Bye, everybody.